Hi, this is Orthogonality Part 2. So inner products and inner products are defined in terms of the summation of the product of each entry of the two vectors involved in the inner product. The order in which they're involved matters, and this formal definition, sometimes you will see in the literature that this is actually called Hermitian inner product. So the definition of inner product, say, between vectors w and x involves a summation of the parts, and you have to be specific here with the vector that appears first in the inner product is the vector that we list first here in the summation, and that vector is the vector to which we calculate the excuse me, the complex conjugate. Okay, so we would write the entries of the first vector w, and say let's use the index j. So we would say here for j, taking values between 1 and m, then this would be wj, but it would be actually the conjugate of wj, and this would be the jth entry of the vector x. So this would be the summation if the order in which they are listed here in the inner product is that one, in which w appears first, the vector is listed first is the vector at which we compute the complex conjugate. However, if you note this in this example, the conjugate of w here would be the conjugate of 2, the conjugate of 4, the conjugate of -3, um, the conjugate of 2 again, and the conjugate of 8. Okay, and so each of these numbers is a complex number that has 0 imaginary part. Therefore, the conjugate of 2 is 2, the conjugate of 4 is 4, the conjugate of -3 is -3, the conjugate of 2 is 2, and the conjugate of 8 is 8. All these are numbers with 0 imaginary parts. You can call them purely real numbers. So when the complex numbers are such that they have 0 imaginary part, the calculation of conjugates is rather straightforward. That makes the calculation of inner products um, for vectors with such type of numbers much straightforward as well. So again, so here is the vector w, and you can see that the entries of that vector are 2, -3, um, excuse me, 2, 4, -3, 2, and 8. They all have 0 imaginary part. Therefore, the calculation of complex conjugates is rather straightforward, and then makes also the calculation of inner product much simpler than when the vectors would have at least one of the entries with a non-zero imaginary part. So in this case, we would say that the inner product between w and x, that inner product is equal to -8. Okay, and so we continue making the point that the inner product is this operator. It takes two entries, right? It takes two arguments that are denoted here as these little rectangles. That means that two things, Cm cross Cm, two vectors of the same length, two vectors from Cm are the arguments of this operator, and what comes out of here is a complex number. -8 is a complex number. You can write this as -8 plus 0 times I, right? So you would say the -8 is a complex number that has 0 imaginary part. But the important thing is two vectors come in, and then one scalar, one complex number scalar, is the output of the inner product. Then the inner product is going to have, as an operator, is going to have certain properties. We can mention some of those properties if uh, we continue making the point, right, that this as an operator has two arguments, okay, two arguments, and these properties have to do with having a sum in one of the arguments. In the first case, there is a sum on argument number 1, and if there is addition on the first argument, that breaks the inner product into the sum of two inner products. Similarly, that happens if the sum is on the second argument. That also breaks the inner product into two sums. You should really think of these scenarios as remember when we had scalars, if you have something like alpha plus beta, and that multiplies, say, a number that maybe we called, I don't know, d, um, the properties of complex numbers would tell us that because of distributivity, right, that would be the formal name of this would become alpha times d plus beta times d. So here, what I didn't write is that there was as scalars, there is a product and there is a sum, and something similar to that is happening in these properties. Um, you know, this operator is called inner product. Part of the name, the last name is product. So there is some type of product or multiplication involved in this operator. You wouldn't really say that this is multiplication of vectors. It's not quite there, but it involves multiplications of the entries of the vectors. And we see in general that the definition of inner product in this way involving the conjugate of a complex number, it involves multiplication of a conjugate in some cases. The other thing to keep in mind here is that we may have also in one of the entries of the inner product, we may have, here's entry number one, argument number two, we may have a scalar. Okay, so what's happening in both of these properties listed under this theorem is that there is a scalar vector multiplication in one of the arguments. In the first property, that happens in the first argument. So we need to be mindful here as to the definition. So maybe we recall this definition of, excuse me, the definition of, say, U, the inner product of U and V. This involves a summation. And here we have the conjugate of U and the entry of V. So this is the conjugate of UK, and the VK entry in here, K runs between 1 and M. Right? So the conjugation is something that is involved in this summation, and therefore, when we say, well, there is a scalar vector product here as one of the arguments of the inner product, we can pull the scalar out of the inner product, but we have to be mindful that it's not just the scalar alone, it's actually the complex conjugate of that scalar. Okay? So, in the order of appearance matters. If alpha u appears as a first argument, if that scalar vector multiplication is in the first argument, what comes out of the inner product is the complex conjugate of the scalar. However, if the scalar vector multiplication appears as a second argument, what comes out is the scalar itself, not the complex conjugate, but the scalar itself. This becomes much easier if the operations are of complex numbers with zero imaginary parts. So if this alpha is a scalar that is a complex number that is purely a real number, it has zero imaginary part, then it really doesn't matter what well, in that case, the conjugate of alpha and alpha, they're both the same. They both have zero imaginary part, and that's what you pull out. But these properties listed here also have to do with something perhaps that you would call at the level of scalars, you would call something similar to common factors, right? These are things that you would pull out of the expression, right? And we write them as factors up front. And something like that is what's happening here, pulling them out of the inner product in front of the inner product. But you have to be mindful. In some cases, you have to conjugate the scalar. In some cases, is the scalar itself that is being pulled out in a similar fashion as to a common factor. So the next property we study here has to do with realizing that if we have two vectors u and v, then their inner product, the order in which they are listed in the inner product matters. Okay, this is telling us that the inner product of u and v in that order, u first, v second, is equal to the conjugate of the inner product of v comma u, where v appears first. So you see there is a reverse. Here v appears second, and now here v appears first. Okay, and so what this is telling us is that the inner product of uv and the inner product of vu, these two things are in general not the same. It is not true that if you switch the order, okay, if you take the inner product of v first and u second, it is not true in general that that inner product is matches or is exactly equal to the inner product of u first and v second. In general, this is not true. If it were true, you would say that this operator is commutative. The commutation or commutativity is preserved. Instead, here, we say that the inner product is not commutative, it's anti-commutative. Okay? And why? So you may wonder, well, anti-commutative, and then you may say, but why is that? Well, let's examine here why. So in a few steps, we can comment why. So here, the inner product of u and v, u appearing first, v appearing second, is equal to this summation where the product of the conjugate of u is listed multiplying the respective corresponding entry of v. We notice that, and this is a property of complex numbers, if we have the conjugate of a complex number and conjugate twice, conjugate of the conjugate is the complex number itself, and therefore we can write this entry v sub j as the conjugate of the conjugate of v sub j. Okay, the properties of complex numbers. Here we notice another property. Say we have alpha times beta, all of which are complex numbers, and then the conjugate of the product is the product of the conjugates. So if we use this property in reverse, we can write these things, this product, as the conjugate of the product of u sub j times the conjugate of v sub j. And another property that's in here, let's say there's alpha and x, and we take the conjugate of these two as scalars. This becomes conjugate of alpha plus the conjugate of x. So the conjugate of the sum is the sum of conjugates. That means that we can take that conjugate outside of the sum, so we can go from that step into the next step due to properties of conjugations, and that tells us that conjugate of the sum is the sum of conjugates. So you're simply applying that property, but in a backward sense. And then once we do that, we can basically flip that v sub j. We can write that v sub j first, conjugate of v sub j first, u sub j second. That's what we do next, right? This conjugation of the sum remains there, but inside the summation, we're simply switching the order of these two things. That's allowed, and then by doing so, we notice that that is precisely the definition of the inner product of v and u, okay, where v appears listed first, and then this bar stays there, so this is the conjugate of the inner product of vu. That's exactly what we have. So we started with the definition of the inner product between u and v. We applied a few properties of conjugation of complex numbers, and then we arrive at concluding that that indeed is equal to the conjugate, notice the conjugate bar over there, of the inner product of VU. So we are, with this, we are proving that inner product is anti-commutative.